Section 19.2, Galvanic Cells. So now what we're going to do is we're going to take a look at what happens when we run a redox reaction, but separate the reactants into separate containers, into separate cells. The example we're going to look at is what happens when we take metallic zinc. Metallic zinc is a solid, right? It's a piece of metal. And we're going to dip it into water and react it with copper 2 ions that are dissolved in the water. A redox reaction will take place, and what will happen is the zinc will get oxidized into zinc ions. And remember, ions dissolve in water. And the copper will get reduced into a solid, into metallic copper. Okay, so ions and elements. Now, if we do that, if we take zinc and put it into one container, copper 2 ions and put it in another container, and arrange it in a particular way so that the reaction is able to run, we will call this a galvanic cell. And let me define a galvanic cell, sometimes called a voltaic cell. A galvanic cell is it's an apparatus, a device that uses a spontaneous reaction to generate electricity. Isn't that cool? We're going to use a redox reaction to generate electricity. Okay? Now, let's go through and let's take this reaction and let's split it up into half reactions. I'm going to show you the oxidation half reaction. And the oxidation half reaction occurs at what's called the anode. Okay? So the oxidation is for zinc, the zinc metal. I'll leave the states of matter out just for simplicity. Will get oxidized into zinc 2 ions, right? Zinc metal gets oxidized into zinc 2 ions. Balance the equation with electrons. 2 electrons on the product side, right? This is oxidation. In galvanic cells, oxidation occurs at what's called the anode, and that'll make more sense to you in a moment. Now, the reduction half reaction is the other metal. That'd be the copper, right? So copper gets reduced, copper 2 ions get reduced into copper metal. Okay, that's reduction. That occurs at what's called the cathode. So there's some terminology we should be aware of. The anode and the cathode are called electrodes. Okay, so the anode, oxidation, and the cathode, reduction, these are called electrodes. Okay? The electrodes are the surfaces where the reactions are actually taking place. And they are actually, what's interesting about a galvanic cell is they're occurring on different surfaces. So the reduction reaction is occurring physically in a different space than where the oxidation is occurring. It's pretty amazing. Okay? So let me show you a picture of a galvanic cell. It's right here. Take a look at that. Okay, the galvanic cell here has 2 beakers. One of the beakers is clear. That has the zinc ions dissolved in it. And there is a piece of zinc metal on the left side of that left beaker. In the right side, the right beaker is blue solution. Now, those are copper 2 ions. Copper 2 ions are blue in water. And the metal dipped into that solution is a piece of copper. So there's two pieces of metal, zinc and copper. The zinc is on the left, the copper is on the right. There are two types of ions. There's the zinc ions and the copper 2 ions. Again, they're in the left and the right. So you're going to put these two species in the same container, and then you're going to put these two species in the same container. But you're going to physically separate them into two different containers. And you can see there are wires connected to those metals, right? The black wire is connected to the zinc metal. The red wire is connected to the copper metal, and they are connected into what is called a voltmeter. A voltmeter measures the electrical voltage. So when I said that electricity is produced, what we mean in this case is an electrical voltage or an electrical potential is generated by the reaction. It's a spontaneous reaction, and the voltage that's being measured is connected very directly to energy. There's energy associated with this. Okay. Now, if you take a look at the display of the voltmeter, it gives the voltage. This is the voltage right here. It's 1.10 volts, V for volts. The volts is on the side there, the V. And so that's the amount of electrical voltage. It is a measure of the electricity that is being generated through this chemical reaction. Okay, so that's what we would call a silver and copper cell. Now, the thing about a voltmeter is that it has a very high electrical resistance. So there is no electrical current flowing through the circuit, or virtually no electrical current flowing the circuit. But if we hook up instead of a voltmeter, a light bulb, for example, or an LED lamp, there might be a low enough resistance in that device that an electrical current will flow through the circuit. In the middle, connecting the two beakers, is what's called a salt bridge. The salt bridge is really cool. It's a requirement for the device to function properly. It bridges the two half reactions, and it can be constructed in different ways. But the one that is displayed here is what's called a glass U-tube, because it's shaped like a U. And it has a piece of glass on either end that allows ions to flow in and out, but not water. Okay, so in here is an aqueous solution. It's actually a saturated solution, meaning there's so much salt dissolved in water, it's actually precipitating out. It's right at the level of the solubility of that particular salt. And there are different salts that can be used. So, for example, KNO3 might be used. Or NaNO3 might be used. Or NaCl might be used. Or KCl. So if you take a look at what could be used in this salt bridge, in that saturated solution, it's these group 1 metals with conjugate bases of strong acids, typically. Okay? That's the idea there. So that's a galvanic cell. Now, you might ask, well, why is this salt bridge there? It's essentially there for the following reason. If you look at what the reactions are that are occurring, without the existence of the salt bridge, a positive charge would develop in the beaker that has, or on the zinc metal, the beaker on the left side, the one that has the zinc solution, a positive voltage would develop there. And that a negative voltage negative charge, not a negative voltage, a positive charge on the zinc metal and a negative charge on the copper metal, and that would stop the half reactions from occurring. So by putting this salt bridge connecting those two containers with a salt bridge, that allows electricity to continue flowing until the reactions have gone to completion. Okay. All right, so let me show you a couple of aspects of how we deal or how we analyze galvanic bridges. Galvanic cells. So for galvanic cells, it is useful and important to calculate what is called the cell potential. And the symbol for that is in capital E, subscript cell, and if it's under standard conditions, we would put the degree sign. So for some of these calculations, it'll be under standard conditions. The cell potential is equal to the potential, the standard reduction potential of the cathode minus the standard reduction potential of the anode. Okay? That's essentially the idea there. So we're going to talk more about that in the next section. But I do want to show you, coming back to the galvanic cell, a type of notation to indicate the structure of this galvanic cell. So instead of just showing half reactions, instead of just showing a diagram, we're going to draw what's called line notation. And this is a common method. So what we do is, we don't know yet why in the picture the zinc container is on the left and the copper is on the right. But there's a reason they positioned it that way. They positioned it that way to be consistent with the line notation. Under line notation, what we do is we use the symbols of the elements that are involved in the reaction. So the two reactants are zinc and copper. So we're going to use those symbols in line notation to represent this galvanic cell. So here's how it works. You put the ionic form of the cathode metal next to these double lines, just to the right of it. And then you put one vertical line next to that, and then you draw the symbol for the cathode. Okay? So in this particular setup, for reasons that we'll see in the next section, copper is the cathode. So you put the symbol for the element, again, this is for the cathode, and then to the left of that, you put the ionic form. The double lines represent the salt bridge. Okay, so that tells you that this is what's happening on the right side, which is the cathode. So the cathode is on the right side. And then what happens on the left side is the anode. Okay, so we're going to do it from the outside in. The metal that we're using for the anode is zinc. So we're going to put zinc on the outside. Let me put aqueous here. Oops, solid. Zinc solid. And then again, just like we did in the cathode side, one line and then the symbol for the ion. I almost put copper 2 again. Okay? So the anode goes on the left, the cathode goes on the right. The only way we know that right now is because I told you the anode was zinc and the cathode was copper. But the electrode, the anode or the cathode, is the metallic form, the solid form in these cases. Okay? Then to the inside, you put the ionic form of that metal, double line for salt bridge. You separate the solid from the aqueous with a vertical line. That vertical line, when we look at that, it has a meaning, a technical meaning. The vertical line means that there is a phase change, a state change. So what happens is we're claiming the salt bridge is in the middle. On the left side is the zinc metal, that's the solid. Next to it is zinc aqueous. And we put a line there to indicate that this is essentially a different state of matter than this one is. This one's dissolved in water. This one is metallic form, solid. And then we do the same thing for the cathode. The metal goes on the outside, the ion goes on the inside, separated by one vertical line. Now, in fact, what happens is, if you think about the salt bridge, it's aqueous down here, where the zinc ions are. It's aqueous over here, where the copper ions are. And then it's saturated ions in here. So in a sense, there's two changes of state. You're going from aqueous to saturated, from saturated to aqueous. So that's why there's two vertical lines to indicate the salt bridge. But most people just say, oh, two lines, that's got to be the salt bridge. Okay? The units of the cell potential are in volts. And we'll talk more about volts when we get into the calculations. In this section, we're not really doing any calculations, but we will claim, for this example, that the measured voltage, the measured potential, is 1.10 volts. So that means that the cathode potential minus the anode potential, of course this is copper and this is zinc, that difference for this example is 1.10 volts. And we'll get more into those calculations in the next section. Okay? Galvanic cells are useful in batteries. That's their main application in industry, is that they can be used to as batteries. They just need to be packaged and engineered properly.